All collisions can be categorized as being either elastic collisions or inelastic collisions. An elastic collision is a type of collision that conserves kinetic energy. In other words, the total kinetic energy of all the particles involved in the collision is going to be the same before and after the collision. Now, just like when we considered conservation of energy and conservation of momentum, it is possible for the kinetic energy of an individual body involved in that collision to change from before the collision to after the collision. However, if I add up the kinetic energy of all the bodies before the collision and add up the kinetic energies of all the bodies after the collision, if the collision is elastic, those total kinetic energies will be the same before and after the collision. Now, this conservation of kinetic energy is only true if we are told the collision is elastic. You cannot assume kinetic energy is going to be conserved. This is not going to be the case in every scenario that you encounter. To a pretty good approximation, billiard balls colliding, marbles, nucleons inside an atom, a really good Super Bowl are all objects that collide more or less elastically. When they undergo their collision, they do conserve kinetic energy. As with every scenario in this course, total energy will always be conserved. Total momentum in both the X and the Y direction will also be conserved. But if you are told a collision is elastic, then you have one more conservation law at your disposal to approach a problem with. A collision that is not elastic is known as inelastic, and inelastic collisions are collisions that do not conserve kinetic energy. Usually when we encounter an inelastic collision, we're going to find that the final kinetic energy is less than the initial kinetic energy. If you think back to the example problem of the skaters Alfred and Barbara, we calculated their total kinetic energy before the collision, we calculated their total kinetic energy after the collision, and we found that they lost about half of their kinetic energy in the collision. So we would say that the skaters colliding and moving off together was an example of an inelastic collision. Within inelastic collisions, there is also the notion of a perfectly inelastic collision. A perfectly inelastic collision is a type of collision where the objects that collide also stick together after the impact. So here are two pictures of some inelastic collisions. We have a person being hit in the face with a pie, and we have a football player tackling another football player. You could ask, if the pie is flying through the air, where does the kinetic energy of the pie go if kinetic energy is lost? Well, there might be some increase in temperature as the atoms get moved around in the pie and as they spread over the person's face. It will probably take some energy to break the pie crust. So those could be some places where kinetic energy is lost. When a football player tackles an opponent, the bodies of the two people are going to contort and they might be pushing against each other. So you might lose energy in the contortion of the shape of the bodies as the football player gets a sack. Some examples of perfectly inelastic collisions could be a record that becomes embedded in a telephone pole after being thrown at it by a tornado, or a tiger that tackles his friend when his friend comes home from school. Before the collision, these objects are separate, they collide. After the collision, they are embedded together, they both move off together with the same velocity. So these would be examples of perfectly inelastic collisions. Newton's cradle is a toy where you pull back a steel ball, you release the steel ball, and to a very good approximation, steel balls colliding will conserve kinetic energy. So steel balls colliding are one example of a type of elastic collision. Now, the steel ball will collide with the next steel ball, that will collide with the next steel ball, and transfer all that energy to the steel ball on the other end of the toy. Then this steel ball on the end will swing upwards, and then it will swing back down and transfer the energy to the ball that was originally pulled up, and it goes back and forth. Now, one thing you might notice is if you pick up one steel ball and release it, you see one steel ball on the other end rise up and come back and fall down. You would never see one steel ball be picked up, drop, collide, and then two steel balls rise up at the other end. And we could investigate with the idea of elastic collisions and momentum conservation why this is. When you use the Newton's Cradle toy, you pull up one steel ball, you let it go, that steel ball will swing down, it will collide with some other steel balls, and one steel ball on the other end of the toy is going to rise up on the other side. You never see a scenario like what I drew here, where one steel ball collides on one end and two steel balls rise up on the opposite end. So the question we're asking is, why do you never see this scenario? In other words, can we prove that this scenario is impossible to actually occur in nature? To address that question, we will consider this scenario in the context of momentum conservation. We will find the relationship between V initial and V final. We will then consider this scenario in the context of kinetic energy conservation. To a very good approximation, steel balls colliding will conserve kinetic energy. That is a very good example of an elastic collision. And we're going to find a different relationship between the initial and final velocities. And so we will come to a contradiction, and that will suggest that this scenario is actually impossible in nature. So we're first going to assume this scenario is possible, and let's apply momentum conservation to this scenario. So the initial momentum of this system would be the mass of the ball that's moving times that ball's velocity. So I would write initial momentum is equal to m times v initial. I only have one ball that's moving, so we will assume all the balls have the same mass m. The final momentum, I could write P final as being equal to mv final plus mv final. In this final case, I have two of the steel balls that are moving. They each have velocity v final, so I wrote it twice. We know momentum must be conserved, so I could set the total initial momentum equal to the total final momentum. So I could write that as mv initial equals mv final plus mv final. And I could cancel out the masses because they're everywhere in this equality. And what I find is v initial is equal to 2v final. So the final velocity of the steel balls is equal to 1/2 the initial velocity of the steel balls. So this will be our result. Momentum conservation tells us V final is equal to 1/2 V initial. Now we will apply the idea of kinetic energy conservation. So the total initial kinetic energy, Ke initial, would be 1/2 times the mass of the steel ball times the initial speed of the steel ball squared. I only have one ball that is moving here, so I only have one term. Here I will have two steel balls that are moving, so I could write Ke final to be 1/2 mv final squared for this steel ball and 1/2 mv final squared for this steel ball. Now I could set the kinetic energies equal to each other because when steel balls collide, that should be an elastic collision. Kinetic energy should be conserved in this interaction. And I find that 1/2 mv initial squared equals 1/2 mv final squared plus 1/2 mv final squared. I could do some algebra on this, and I'll first cancel out the m's everywhere. I'll also cancel out the factor of 1/2 everywhere. And I'm left with v initial squared equals to v final squared. And if I solve for v final, I get v final is equal to 1 over square root 2 v initial. So what we found here is momentum conservation tells us that the final velocity of the steel balls is going to be half the initial velocity of the steel ball that's moving. Kinetic energy conservation tells us that the final velocity of one of these steel balls is going to be 1 over square root 2, the initial velocity of the steel ball that was falling. Now, both of these cannot be true, and the resolution to this is that kinetic energy should be conserved and momentum should be conserved, but this assumption that you have one ball falling and 2 steel balls rising, this is physically impossible to see in nature.